Good evening all and welcome to TH GENCO Electrical Engineering Score Booster Series by ACE Engineering Academy and ACE Online. Okay. So friends, you might be knowing from last few days the ACE Academy has started this Score Booster Series. Okay. Already few subjects completed. Now today's subject is power electronics, right? Power electronics. Myself, Rajendra Gharase, I have done M.Tech from Indian Institute of Science, Bangalore. I was All India 7th ranker in the GATE examination, and currently I am working as a faculty at ACE Engineering Academy, Hyderabad. So friends, in this session, we are going to have some overview of power electronic important topics, and we will be discussing some important questions also. Okay, right. So this session will be interactive session. Okay, so please try to answer the questions. Okay, right. So let us have some discussion on syllabus. So as long as TH GENCO is considered, we are having the topics like power semiconductor devices. This topic deals with the study of semiconductor devices like your power diode, power BJT, power MOSFET, IGBT, GTO, TRIAC and SCR. But SCR in depth analysis we are having in syllabus. All other remaining switches only introductory part. So on other switches except your SCR, on all other switches you can expect only theory question. Okay, right. Second is the AC to DC converter. So whatever the power semiconductor devices we are going to discuss in the chapter 1, all these devices or some of these devices we are going to use in the converters. Chapter 2nd onwards we are having only converters. Okay, AC to DC converter, one of the vast chapter of power electronics. Third is the DC to AC converter. It is also known as an inverter. Fourth is a DC to DC converter. It is also known as a chopper. Fifth chapter is AC voltage controller, right? Sixth is a cycloconverter, and seventh is the fundamentals of electric drive. So these chapters we are having in syllabus. But based on the previous year questions, if we check, the maximum questions you will be getting on only first 4 chapters. Comparatively very less questions you will be getting on remaining 3 chapters. Okay, so more questions on these 4 chapters. So these 4 chapters are very important. All right. So let us now discuss one by one power semiconductor devices. Which are the important points you are required to prepare in this chapter? Let us discuss. So first is piecewise modeling of devices and conduction loss expression. We know in piecewise modeling of devices means when a practical device is in a conduction mode, then it is represented in 3 models. In that first model is a pure resistor, right? First modeling is a pure resistor like a Ron. Second modeling is constant voltage drop. Second model is a constant voltage drop, right? VT. And third modeling is a combination of these two, means VT in series with Ron. VT in series with Ron, right? VT and Ron. So these 3 models we are having. Generally MOSFET during on state is represented as pure resistor, right? MOSFET during on state is represented as a pure resistor. In some of the examinations, this question they have asked, during on state the MOSFET is equivalent to resistor, inductor, capacitor, etc. So your answer should be the resistor. Power BJT or BJT during on state is represented equivalent to the constant voltage drop. And all other switches except your MOSFET and BJT comes under the third modeling. Okay. So all other switches like SCR, your diode, GTO, right, etc. All this comes under the third modeling, right? So for every modeling we are having a power expression. Na? For first modeling, that is Ron. What is the power expression? I am writing here. I RMS square into Ron. I RMS square into Ron. You can expect a question on average on state power loss in a device. Okay, right. So for the first modeling, what is second modeling power loss expression? P average. For second modeling, P average is equal to Vt in series Vt into I average. And for third modeling, it is the addition of these two, na? Because third modeling is Vt in series with Ron. So therefore power loss P average is equal to addition of these two, right? So I am writing here P average is equal to I RMS square into Ron. I RMS square into Ron plus Vt into I average, right? Vt into I average. All right? Yes. So this is about the piecewise modeling of devices and it's a power loss, conduction state power loss. Okay, you can expect question on conduction state power loss. Next, second important point is a power diode. As long as power diode is considered, you can expect a theory question, okay, and numerical question on only dynamic characteristic of power diode. Dynamic characteristic. In dynamic characteristic, we are having that expression for QRR, na, reverse recovery charge. That is nothing but area under the triangle and those things. Okay, so please go through that dynamic characteristic of power diode. Okay, you can expect the question. Okay, next, and other only theory questions you can expect. Next important is a SCR. In SCR, we are having the various points. So from that, which are the important points that we are going to discuss. Here, minimum width of the gate pulse required. If you check SCR, we know SCR is a semi-controlled device. Once SCR turns on, after that the gate signal is not required. Alright. So, minimum width of the gate pulse required, right, given the latching current. Okay, they have asked some questions. So, please, this minimum width of the gate signal means TP. These type of questions for which type of load? Purely inductive load. Right, purely inductive load. You can expect a question on purely inductive load. Okay, on RL load there is a less possibility of getting question on RL load because for these type of examinations calculators are not allowed. If you go for the RL load, then your calculation will become difficult. Okay, you will be getting the current expression in terms of some e to the power. So that's why very less chances of getting question on RL load, but on purely inductive load you can expect a question. Okay, you can expect a question, right? Next, so minimum width of the gate pulse. Next is SCR protection. Yes, very important. In SCR protection, over voltage protection, over current protection, high du by dt and high di by dt protection. So for protection of over voltage, which element or which device is used? For protection of over current, which device is used? Okay, those are important. So we are having over voltage protection. Yes, in short I am writing here over voltage. For over voltage protection, which device we are using? Varistor. We are using varistor, right? Second, over current protection. Over current protection. For over current protection, we are using fast acting current limiting fuse, that is FACLF, and circuit breaker na, and circuit breaker we are using. Next, high dV by dt protection. High dV by dt protection. For high dV by dt, how to protect? RC snubber circuit. RC snubber circuit. And high di by dt. For high di by dt, yes, inductor is used. Alright, inductor is used. Inductor is used. Is this clear? Right? So these are the main protections of the SCR. Again, apart from that, we are having the gate cathode circuit protection also. Okay. So generally, they have not asked the questions on gate cathode protection, but maximum questions only on these four you can expect. Some theory question you can expect. Okay. Right. Next, thermal modeling of SCR. Right. Thermal modeling is used in order to design the heat sink. Okay. So in thermal modeling, we are having one circuit na. That circuit is important. Right. How we represent thermal modeling of SCR? We are having a circuit like this. P average. And here we are having the thermal resistances. So only this circuit is important. P average Yes. This is TJ, TC, TS and TA. And the thermal resistance between junction and case, that is a theta JC, theta CS and theta SA, right? Only this circuit is important, okay? From this circuit you can easily write the expression for P average. P average is temperature difference upon this thermal resistance or thermal impedance, okay? So this circuit is thermal modeling of SCR. You can expect a question on thermal modeling of SCR. Next is other switching devices. On other switching devices, you can expect only theory question. Other switching devices are power BJT, power MOSFET, IGBT and GTO. Yes, TRIC is also there, TRIC, okay? So on these devices you can expect only theory question you can expect, alright. So these are the important points from chapter number 1, right. Now let us move towards the second chapter, chapter number 2. We know chapter 2 is a very vast chapter, right. Too much concept is there, too much contents are there. So from this, which are the important points, which are the important circuits, which are the important loads you need to focus, let us discuss, okay. So here, single phase half wave rectifier. In single phase half wave, we are having uncontrolled rectifier and controlled rectifier, okay. So in that, focus only on resistive load and purely inductive load. Resistive and only purely inductive, right. Don't go for REL load, RE load, not required, okay. So on purely inductive also some specific questions they have asked. On purely inductive, you can expect the question on conduction angle of diode. Conduction angle of a diode, or if it is a controlled, then it is conduction angle of SCR, right. Only question on conduction angle of diode or SCR you can expect on purely inductive, okay. And on purely resistive, simply go through that what is V0 average expression, okay. Here circuit turn up time and those things are not required, that much depth they have not asked in a GENCO examination, okay. So only resistive load and inductive load you can focus, and in inductive only important is conduction angle of diode, okay. Repeatedly they have asked the question on single phase half wave. Second is single phase full wave rectifier. In single phase full wave rectifier, yes, focus on purely resistive load, purely resistive load, RL load, RL load, with and without freewheeling diode. In full wave, my RL is nothing but highly inductive only, highly inductive, that is load current is constant, highly inductive, that is load current is a constant, okay. Next, R load, RL with and without freewheeling diode, and next one is a RL E load, RL E load. RL E is again highly inductive only, highly inductive. Please focus on only on these three loads, only on these three loads, okay. Very less possibility of getting question on RE load, okay, right. So need not to worry, only these three loads you need to focus. Next, for RL load or RL E load, that is when load is highly inductive, then in single phase full wave, in that we are having the bridge rectifier, na, right. Single phase full wave, that is a bridge rectifier. In bridge rectifier, what is the nature of source current is important. For RL and RLE, nature of source current waveform is important. If you recall my source current waveform, how it is? For highly inductive load, single phase bridge rectifier, my source current is a square function. Yes or no? Source current is a square function. Alright? Yes. Next, single phase semi converter. Yes, single phase semi converter. Semi converter means here we are using two thyristors and two diodes. Okay. On this also only highly inductive load, RL or RLE, and only highly inductive load. In this case also, what is the nature of source current? That is important. IS, source current. In semi converters, my source current waveform is a quasi square function. In full converters, that is a full wave rectifier, that is full converter in bridge rectifier, my source current is a square function. Here source current square function, here source current is a quasi square function. Okay, quasi square function, right? Apart from that, for highly inductive load, please go through the conduction angle of diode, right? They have asked some questions. Diode conducts for dash dash angle. Okay, right. Next, inverter mode operation of converter. Yes, inverter mode operation of single phase full converter. Yes, for inverter mode operation, what are the required conditions? Those are important. Alpha should be greater than 90 degree, right? Next, EMF should be reversed. That is, E should be negative. E should be negative, and E value should be greater than supply voltage. E value should be greater than supply voltage. These are the required conditions. On these conditions, they have asked the question, okay, in inverter mode operation. Next, three-phase half-wave rectifier, okay. Three-phase half-wave means here we are using the three thyristors, okay, right. On three-phase half-wave, for R load, what is the V0 average expression? Please memorize this expression. V0 average expression, please memorize it, okay. Yes, it is a 3 VML upon 2 pi into cos alpha. Same expression is there for RL also. Same expression is valid for RL load also. RL load, okay. So for three-phase half-wave, this expression you are required to memorize, right? Straightforward, based on the expression, they have asked the question, okay, right. Next, three-phase full wave rectifier. In three-phase full wave rectifier, yes, specifically for highly inductive load, RL, highly inductive load. What is the waveform of supply phase current? Supply phase current waveform, supply phase current waveform, and thyristor current waveform, and thyristor current waveform. These two waveforms are important. Straightforward, based on that waveform and expression of RMS value of that current, they have asked the expression. They have asked the question. Okay. In one of the examination, they asked the question: three-phase full converter feeding to highly inductive load. What is the RMS value of supply phase current? What is the RMS value of thyristor current? Okay. So please go through those waveforms and what is the RMS value expression. You are required to memorize, right? Next. Similarly here for three-phase full converter, my output voltage expression is the same 3 VML upon pi into cos alpha. In this case it is 3 VML by 2 pi cos alpha. Here it is 3 VML by pi into cos alpha. Please understand the changes. Here it is 2 pi, here it is pi, right? Here it is pi. Next, three-phase half wave, it will give you 3 pulses in output. So that's why this is known as a 3-pulse rectifier. This is a 6-pulse rectifier. Full wave is a 6-pulse rectifier, right? 6-pulse rectifier. Next, three-phase semi-converter. On three-phase semi-converter, very less questions they have asked. Okay? Only thing is here, conduction angle of diode. Conduction angle of diode. Angle of diode means freewheeling diode. DF means a freewheeling diode. Okay, that is important. Conduction angle of freewheeling diode. Again, in that we are having alpha less than 60 degree, alpha greater than 60 degree. Two different expressions, less than or equal to 60 and greater than 60. Two different expressions we are having. Okay, so please try to go through those expressions. Okay, you can expect the question. Next. Yes. Input power factor for highly inductive loads. Yes. For highly inductive load, input power factor expressions. Yes. If you are having a single phase full converter, single phase full converter, then we find how to find the input power factor. We are having the input power factor is equal to DF into DPF. DF into DPF. DF means distortion factor. DPF is displacement power factor. Okay. So for single phase full converter, single phase semi converter, 3-phase full converter and 3-phase semi converter. We are having the expression for DF and DPF. Okay, so please try to go through those expressions. Okay, here 3-phase semi converter expressions are not required to memorize because till now not a single question they have asked. Only important expressions you need to memorize are single phase full converter, 3-phase full converter and single phase semi converter. Single phase semi converter, right? Directly they have asked the question, what is the input power factor of 3-phase full converter feeding to highly inductive load if alpha is so and so? Okay, so please go through those expressions, those are important. Yes sir, please provide me rectifier, converter and inverter notes if you have. I will provide the notes also. Yes, at the end of this session I will give you my contact number. You can send me message on WhatsApp or you can email me. I will share you the notes. Okay, right. And formula sheet also I will share, particularly for this chapter, because in this chapter we are having the n number of circuits and for every circuit we are having the various loads, right? So number of expressions are there, but from that which expression you are required to memorize. As long as TH GENCO point of view, which expressions are important, those expressions were taken in that formula sheet. Okay, yes. So input power factor for highly inductive load. Okay, and next is the effect of source inductance on converter. What is the effect of source inductance? Means output voltage decreases, right? If source inductance is present, then what is the displacement power factor? This type of question they have asked. Okay, so I am writing here, overall effect of your source inductance is output voltage of converter decreases, output voltage of converter decreases, and my displacement power factor, or it is known as a fundamental power factor, is equal to cos of alpha plus mu by 2. Alpha plus mu by 2. In one of the examination, like GENCO Transco, they gave the overlap angle mu, they gave the alpha, and they asked what is the displacement power factor when source inductance is present. So only this expression you are required to use. Okay, right. So these are the important points from AC to DC converter. Okay, at least these points you are required to prepare. Okay, minimum. If you prepare over and above, that will be good, but minimum you are required to prepare these points. Okay, because there is a high possibility of getting question on these points. All right. Next, last one is a dual converter. On dual converter you can expect only theory question, right? So what is a dual converter? Dual converter. In dual converter, two full converters are connected in anti-parallel, anti-parallel, or it is also known as back-to-back, anti-parallel or back-to-back, right? Regarding the dual converter, one expression is important. Alpha A plus alpha B is equal to 180 degree, or cos alpha A plus cos alpha B, cos alpha A plus cos alpha B is equal to 0, right? Is equal to 0. These expressions are important. Okay, so based on this they have asked questions even. Next, so these are the important points related to the AC to DC converter. Okay, in short I am trying to give you the important points here, because we are going to discuss some numerical problems also. Okay, yes. In DC to AC converter, first thing is you should not keep this chapter as an option. You should prepare this chapter because very less contents are there in this chapter, and in DC to DC converter also very less contents are there, but weightage is good, right? So you should prepare this chapter. Okay, so DC to AC converter, in that single phase half bridge inverter. In single phase half bridge inverter, yes, R load and L load. Focus only on these two loads. Okay, R load and L load. Okay, and in half bridge inverter as well as in full bridge inverter, in half bridge as well as in full bridge inverter, focus on these two loads. Here for purely inductive load they ask the questions like what is the conduction time of each thyristor, each diode, or each switch and each diode. So for L load conduction time of each switch and each diode, is simply, it is T by 4 is equal to T by 4. Next, in single phase inverters, these are voltage source inverters na, so output voltage is independent of nature of load. For all loads my output voltage is a square function. For all loads output voltage is a square function. But load current depends on the load, right? Means I0, if load is resistive, then my load current is a square function. If load is inductive, then load current is a triangular function. It is a triangular function. And if load is RL, then my load current is a exponential rise, exponential fall. Exponential rise and exponential fall type function, right? Fall type function. So they asked the question specifically on inductive load. Single phase full converter feeding to purely inductive load. The nature of load current is, so your nature of load current is a triangular. In resistive load it is a square function, okay? On RL load as such you will not find a equation, okay? So these two are important, R load and L load. Next, in half bridge and full bridge inverter, the Fourier series expression of output voltage. Fourier series expression I am writing here. Half bridge as well as full bridge. Fourier series expression of output voltage. This expression you are required to memorize, right? They have asked the question, RMS value of fundamental component of load voltage, that is V01 RMS, okay? So expressions are important. Half bridge and full bridge, Fourier series expression for output voltage, all right? Next, three-phase inverter. Yes. So in three-phase inverter, we know we are having a 180-degree conduction mode and 120-degree conduction mode. 180-degree and 120-degree mode. 180-degree mode and 120-degree conduction mode. Okay. On three-phase inverter, very simple question they have asked. Those questions are directly related to your circuit diagram only. So here operation table is important. Operation table, right? You are not required to memorize that V0 RMS expression, that is RMS value of phase voltage, RMS value of line voltage. You are not required to memorize. They have not asked the question. Some simple question they have asked on a three-phase inverter, right? If switch sequence is, if you recall our circuit diagram, we are having upper group switches are S1, S3, S5 and lower group are S4, S6, S2. So instead of that, suppose if they give the switch sequence like S1, S2, S3 and S4, S5, S6 in lower group, then how will be your operation table sequence of your devices, conduction sequence of devices? Those type of simple question they have asked, okay? Yes, we'll discuss, okay? If time permits, we'll definitely discuss. Next, so in three-phase inverter, you are required to only focus on operation table, right? Fourier series expression you are not required to memorize on three-phase inverters. Phase voltage, line voltage, RMS value expressions are not required to memorize, okay? Operation table is important, okay? Right. Next, pulse width modulation. And one more thing in three-phase inverters, yes, one ratio is there, P0 120 upon P0 180, which is equal to 0.75. What it indicates? If I use 120-degree conduction mode, then my load power, right? And if I use 180-degree conduction mode, then my load power. So ratio of these load powers for 120-degree conduction mode and 180-degree conduction mode is a 0.75, okay? So one of the examination they ask the question, for 180-degree if my load power is 10 kilowatt, then for 120-degree what is the load power? So for that you can use this expression here, okay? Right. So very less questions you can expect. Next, pulse width modulation technique, important bit, pulse width modulation technique. In pulse width modulation, single pulse width modulation, single PWM, right? In that your V0 RMS expression, V0 RMS expression is important, right? What is V0 RMS expression? It is under root 2D by pi into Vs simply. 2D is a pulse width. 2D is a pulse width. Next, in single PWM, for elimination of the particular harmonic, what is the pulse width required, right? For elimination of nth harmonic, for elimination of nth harmonic, yes, required pulse width is a 2 pi by n. In general, it is a 2 pi by n. Okay, so they ask the questions like for third harmonic elimination, what is the required pulse width? For fifth harmonic elimination, what is the required pulse width? Third harmonic elimination means n is equal to 3, so pulse width is 2 pi by 3. Fifth harmonic is 2 pi by 5, okay, etc. So they have asked the question on third harmonic and fifth harmonic. On seventh harmonic, they have not asked the question, okay, so need not to worry, only focus on third and the fifth harmonic, So important points from single PWM. Multiple pulse width modulation technique. Multiple PWM. Yes, on multiple PWM, output voltage expression V0 RMS is important. Okay, what is output voltage expression? It is under root n into 2D by n upon pi into Vs. N means number of pulses per half cycle in inverter output. 2D by n is a width of each pulse, okay, and under root of this divided by pi into Vs, okay. Less questions they have asked on multiple PWM, more questions you will find on single pulse width modulation technique, okay. And next we are having the sinusoidal PWM. On sinusoidal PWM, very less questions they have asked, okay. But what is the harmonic contents, most dominant harmonic frequency, this type of question they have asked, okay. But maximum questions you can expect on single and multiple PWM. And apart from that, we are having the one more bit, current source inverter. On current source inverter, less questions they have asked, but here I am only adding the important points. In current source inverter, output current is independent of load. I0 is independent of load. Independent of load. And V0 depend on load. V0 depend on load. It is opposite to that of voltage source inverter. In voltage source inverter, what we wrote? V0 is independent. For all loads, V0 was square. But in current source inverter, my I0 is independent of load. For all loads, my load current is a square function. For all loads, I0 is a square function. Square function. Whereas my V0 depend on load. If load is resistive, my V0 is a square function. For R load, it is a square. For C load, purely capacitive load, my V0 is a triangular function. Triangular function. And for RC load, it is exponential rise, exponential fall. Exponential rise and exponential fall. And exponential fall, all right, exponential fall. Okay, so on current source inverter, less questions they have asked, but you can expect some theory question, right? What is the nature of current, load current, load voltage for particular load, okay, right. Next, so these are the important points from DC to AC converters, okay. Next, DC to DC converter. In DC to DC converter, basic chopper circuits, that is step down, step up, and step up, step down. Step up, step down. These are the three basic chopper circuits, right? Three basic chopper circuits. In these chopper circuits, output voltage expression V0. For step down, what is V0? D into Vs. For step up, it is a Vs upon 1 minus a D. And for step up, step down, V0 is equal to Vs d into Vs upon 1 minus d. Okay, so these expressions are important as long as basic chopper circuits are considered. Okay, right. Next we are having the switched mode power supplies like a buck converter, boost converter and buck boost converter. In buck converter, boost converter, buck boost converter, in depth analysis we are having, but your GENCO transco is considered a very less questions they have asked and some questions directly related to your expressions they have asked. So which expressions you are required to memorize for buck boost and buck boost converter? I am writing here. Delta IL, ripple in inductor current, delta IL expression you are required to memorize. Okay. Next delta VC expression, next IL average, next maximum value of inductor current, minimum value of inductor current, right? These expressions you are required to memorize. Okay, right. So they have asked the question on delta IL, delta VC. Some theory questions also they have asked. Okay, so for these three converters we are having the expressions for delta IL, delta VC. For boost and buck boost, if you check, my delta IL expression is same. Boost and buck boost, my delta VC expression is also same. Okay, so only these expressions you can go through it. Okay, right. Next, types of the choppers based on the quadrants of operation. So simple types we are having type A, type B, type C, type D and type E choppers na. So from that, which chopper is related to which quadrant, that you need to understand. Type A chopper operates in a first quadrant. Type B chopper second quadrant. Type C first and second. Type D first and fourth. Okay. Type E is all four quadrants. Okay. So please go through it. Which type is of the chopper is operates in which quadrant? Some questions they have asked. Type A chopper operates in dash dash quadrant. Type D chopper operates in dash dash quadrant. Okay, only theory question you can expect on these types of the choppers. Next to that important bit is thyristor commutated chopper. In that, voltage commutated chopper is very important. I am saying very important. Voltage commutated chopper. Multiple times in your TS GENCO, TS transco they have asked the question. On voltage commutator only. Current commutated chopper they have not asked the more questions. Very rarely they have asked. But on voltage commutated chopper, large number of questions you can find. Refer your previous examination papers. More questions they have asked on voltage commutated chopper. In that also, the peak value of current flowing through the main thyristor, IT1 peak. Right? What is the expression for IT1 peak? It is equal to I0 plus Vs under root C by L. Next, peak value of capacitor current, IC peak, which is equal to Vs under root C by L. Right? Peak value of auxiliary thyristor current, ITA peak, which is equal to I0. Right? Only on a peak value of currents they have asked the question. Okay? Circuit turn off time, output voltage, average value, they have not asked the question. Okay, so important points are only these three: IT1 peak, IC peak, ITA peak. In addition, please try to memorize minimum on time of SCR. Minimum on time. I am trying to give maximum from my side. Minimum on time of thyristor T1 is equal to pi by omega 0. And what is omega 0? 1 by root LC, right? 1 by root LC. Okay, so these are the important expressions from voltage commutated chopper. In chopper, this bit is chopper chapter. This bit is very important. Okay, right? Because high possibility of getting question on voltage commutated chopper. Very less questions they have asked on a current commutated chopper. Okay, so if you want, you can simply skip this current commutated, but voltage commutated is very important. All right. So these are the important bits from DC to DC converter. Next, AC voltage regulator, or it is also known as a AC voltage controller. In AC voltage controller, only we are having the three circuits. First one is, yes, integral cycle control. Integral cycle control. From that important expressions I am writing here. Yes, V0 RMS is equal to root K into Vs RMS. What is K? K equal to N upon M plus N. This is known as a duty cycle or duty ratio. duty cycle or duty ratio, right? So these two expressions are important, okay? And what is input power factor? Input power factor is also equal to root k, is equal to root k. So integral cycle control. Second one is a phase control. Integral cycle control is also known as on-off control. On-off control. And second one is a phase control. Okay, phase control. In phase control only single phase full wave AC voltage controller. AC voltage controller, or it is also known as single phase bidirectional. Single phase bidirectional AC voltage controller. AC voltage controller. Yes, AC voltage controller, right? So this circuit is important. Only this circuit is important. Okay. Yes. So in this we are having range of firing angle. Range of firing angle alpha for getting controlled output. For getting controlled output. If load is resistive. If load is resistive, what is the range of firing angle? 0 degree less than equal to alpha less than 180 degree. If load is purely inductive, the range of firing angle is 90 degree less than equal to alpha less than 180 degree. And if load is REL, then it is phi less than equal to alpha less than 180 degree. What is phi here? Phi is nothing but tan inverse of omega L by R. Tan inverse of omega L by R. All right. Yes. So range of firing angle for getting controlled output. For getting controlled output. All right. Yes. So these are the important bits from single phase full wave AC voltage controller. Okay. Next, if load is resistive, then conduction angle of SCR. Yes. Conduction angle of SCR is equal to pi minus alpha. If load is purely inductive, then it is a 2 into pi minus alpha. Conduction angle of SCR is a 2 into pi minus alpha. All right. So in AC voltage controller, you are required to focus only on these two circuits, integral cycle control and phase control. In phase control, these are the important points. Okay. Next, you can expect less questions on AC voltage controller. Next is a cycloconverter. In cycloconverter, we are having yes, midpoint type cycloconverter. Midpoint cycloconverter and bridge cycloconverter. Bridge cycloconverter. Comparatively less questions you can expect on cycloconverter, midpoint and bridge cycloconverter. Please go through the circuit diagram and its operation. Again, we are having the types based on the number of phases. Single phase to single phase, 3 phase to single phase, and 3 phase to 3 phase. So some question they have asked, in 3 phase to 3 phase cycloconverter, what is the number of SCRs required? In a 3 phase to single phase cycloconverter, what is the number of SCRs required? Please go through this. Number of SCRs required. Number of SCRs required. Okay. Some questions you can expect on number of SCRs required. Okay. Right. Next is a step up cycloconverter and step down cycloconverter. Step up and step down cycloconverter. So in step up cycloconverter, which commutation is used? Force commutation. Here it is force commutation. Whereas here natural commutation. Natural commutation. Okay. natural commutation. Yes, so these are the important bits from cycloconverter. Okay, right. Next, fundamentals of drives. Only fundamental part is there. On drives you can expect a numerical question, but some simple numerical. For solving the drive questions, you should have the information about the output voltage expression of a converter. Suppose if they give the DC motor as a load, and suppose the converter is single phase full converter, then for single phase full converter, when the load is RLE, highly inductive load, then what is the V0 average expression? That you should know. What is V0 average expression for single phase full converter? 2 Vm by pi into cos alpha. This is for single phase full converter. For single phase semi converter, the expression is Vm by pi into 1 plus cos alpha. This is for single phase semi converter. And for 3 phase full converter, it is 3 VML by pi into cos alpha. Right? 3 phase semi converter, it is 3 VML by 2 pi into 1 plus cos alpha, etc. Right? So single phase full, single phase semi, 3 phase full, 3 phase semi. These are output voltage expressions of your converter. Some simple question they asked. 3 phase full converter feeding to DC motor load. If the converter is operating at alpha equal to 45 degree, then what is the output voltage expression? They will give the supply voltage value, line voltage, etc. And they will give the alpha value also. So simply by using this, you can find your V0 average, that is output voltage of your converter. Right? In drive, output of converter is given as an input. Output of converter is given as an input. Given as an input to motor. Input to motor. So from motor also you require some concepts, that is back EMF. In DC motor, back EMF is proportional to flux into speed, and torque is proportional to flux into armature current. Okay. So by using these two expressions and these output voltage expressions of the converter, you can solve the numerical related to the drive. Okay, right. Some less questions you can expect on a drive. Okay, right. So maximum questions you can expect on first 4, right? Only on first 4 bits, right? First 4 bits. Yes. Let us discuss now some numericals. Yeah, some questions. Come on, you can post your answers in a chat box also. Okay, some simple questions are there. A charger supplies 100 watt at 20 volt for charging the battery of a laptop. The power devices used in the converter inside the charger operate at a switching frequency of 200 kilohertz. Switching frequency of what is 200 kilohertz. Which power device is best suited for this purpose? Yes, can anyone? My switching frequency is 200 kilohertz. So from this, which device is suitable? That we need to find. Come on. You can post your answers in the chat box. Yes, MOSFET is preferred, na? MOSFET. What happens here? Operating frequency of MOSFET or power MOSFET, you can say here, is up to 1 megahertz. For IGBT, operating frequency is up to 10 to 20, for IGBT is 50 kilohertz. 50 kilohertz. And for BJT or power BJT, it is up to 10 to 20 kilohertz. So here they are asking the frequency of 200 kilohertz. So any frequency which is greater than 50 kilohertz, only one possibility we are having, that is equal to MOS, that is nothing but MOSFET. Okay. So here suitable switch is a MOSFET. Option C is the correct option. All right. Yes. Next, the MOSFET switch in its on state may be considered equivalent to. MOSFET during on state is represented as first piecewise modeling na, that is a pure resistor, right? Next, yes, the triac can be used only in, yes, in which converters we use triac? Do we use triac in inverters? No. Do we use triac in rectifiers? No. Do we use triac in multi-quadrant chopper? No. We are using triac only in AC voltage controllers and cycloconverters. Triac are used in AC voltage regulator or AC voltage controller, or it is also known as a regulator. And yes, it is used in a cycloconverter, right? SCRs and a triac, these are the switches. Those can be used, or those are used in the converters where input is AC. Okay, but in rectifiers I use the SCRs, and in a AC voltage regulator or cycloconverter, there we require the bidirectional na, so that's why we go for the triac. Okay, so correct answer is option D. Option D is the correct option. Next, which of the following does not cause permanent damage to an SCR? Yes, during our classroom sessions we have discussed this question. Which of the following does not cause the permanent damage to an SCR? High current, high rate of rise of current, high temperature rise, and high rate of rise of voltage. Does not cause. So high current will definitely cause the permanent damage. So does not cause. This is not the correct answer, right? High rate of rise of current, high di by dt, high di by dt will cause your local hotspot, creation of local hotspot in your SCR. So my SCR may get damaged permanently, right? Next, high temperature rise. Every semiconductor device is having some temperature withstanding capacity. If your temperature of the semiconductor device goes beyond allowable temperature limit, then your device may get damaged permanently. High dV by dt, rate of rise of voltage, right, means high dV by dt. At high dV by dt, what happens? My device will only false trigger. Device will not get damaged. The device will only false trigger, right? Device will only false trigger. So correct answer is option D. Option D is the correct option. Remaining 3 will cause the permanent damage, but here high dV by dt will not cause the permanent damage. All right. Next, in a commutation circuit employed to turn off an SCR, satisfactory turn off is obtained when? Yes, for satisfactory or successful turn off, successful commutation of SCR, what is the required condition? Circuit turn off time and device turn off time they are asking. Yes, post your answers in the chat box. Yes, for a successful commutation, what is the requirement? TC should be greater than or equal to TQ. TC means circuit turn off time, and TQ is device turn off time, all right, device turn off time. So for successful commutation, circuit turn off time should be greater than or equal to device turn off time, circuit turn off time greater than device turn off time. So option B is the correct option. Option C is the circuit time constant. They are saying your time constant is not having any relation with your device turn off time. Okay, so correct answer is option B. All right, option B is the correct option. Next, circuit turn off time of an SCR is defined as the time. What is the definition of circuit turn off time? It is a time during which reverse voltage is maintained across SCR, right? So option A is taken by SCR to turn off. No. Required for the SCR current to become 0. No. For which SCR is reverse biased by the commutation circuit, and for which SCR is reverse biased to reduce its current below holding current. No. So option C is the correct option. Reverse voltage is maintained, that is reverse biased, and who is maintaining that reverse voltage? Commutation circuit, right? So option C is the correct option. Next, yes, figure shows 4 electronic switches 1, 2, 3 and 4. Which of the switches can block voltages of either polarity applied between terminals A and B when the active device is in off state? Yes, when active device is in off state, which devices block the voltages of either polarity, they are asking. Either polarity means forward voltage and reverse voltage, means they are asking bipolar. Which of these 4 switches are, yes, which of these 4 switches are bipolar switches, they are asking. Out of these 4, which are the bipolar? Yes, can anyone? You can post your answers in the chat box. Always keep in mind, if you are having this type of diode connection, when the diode is connected in anti-parallel with your active device, right, then your composite switch will not be able to block that reverse voltage. What happens? Because of diode, when I maintain the reverse voltage here, plus here, minus here, this diode will immediately start conduction. So therefore my composite switch will not block that voltage. Okay, so when diode is present, reverse voltage blocking is not possible. Okay, but in this case, check second and third switch. They can block forward voltage when active device is in off state, and when reverse voltage applied like this, plus here, minus here, then this diode will block this reverse voltage. So this is a bipolar. What about this one? This is simple SCR, na? This is not a composite switch. SCR is a simple switch, and we know SCR is a bipolar device. So therefore 2 and 3 is the correct answer. Okay, 2 and 3 means option C. Option C is the correct answer. All right? Yes. Yes. Next, the gate triggering circuit shown below has the specifications. They have given this circuit, and here the minimum gate current required to turn on SCR is 100 milliampere, and VG mean is 2 volt, right? So what is the V trigger? That is trigger voltage they are asking. Trigger voltage means this voltage they are asking. V trigger. So this is simple network theory problem. VG means this voltage. This is my VG. And IG is this current. IG is this current, right? Now, to turn on the SCR, how much voltage required here? 2 volt, na? So this voltage is now 2 volt. This voltage is 2 volt. Tell me, if I am having the voltage here 2 volt with the polarity plus here, minus here, what is the status of my diode? When the voltage is plus here, minus here 2 volt, then what is the status of diode? It is like a higher potential at a cathode, lower potential at a anode. Diode will be in a reverse bias mode, na? Diode reverse means no current will flow in this branch, right? So can I say that if here current is Ig, that is nothing but Ig mean, same Ig mean will flow here also. Same Ig mean will flow here also. Yes or no? Right. Next, how much current will flow through this resistor? Tell me, if this voltage is 2 volt, what is the voltage across this resistor? Same 2 volt, na? Check, this voltage is 2 volt. Diode is off state now. So this is 2 volt means same 2 volt will appear across this resistor also. So from this I can find the current flowing through the resistor, na? Let me write that current as I1. I1. Yes, I am writing that current as a I1. And what is the current flowing through this branch? This branch current is Ig mean plus I1. This current is Ig mean plus I1. So I can write now V trigger is equal to simply this voltage is 2 volt plus voltage across this 30 ohm resistor. What is voltage across 30 ohm resistor? According to Ohm's law, it is 30 into this current, na? Current is Ig mean plus I1. Ig mean plus I1. Now what is I1? I1 is simply, it is 2 by 30, na? I1 is 2 upon 30, right? So I can write it as 2 plus 30 into Ig mean they have given 0.1 ampere plus this is 2 by 30. You can simplify this and you can find the V trigger, right? V trigger. I think after simplification, you can get it as a 7 volt. Yes, right? So simply this is a network theory problem, strictly speaking, okay, because this voltage they have given here, right? Next, yes, what is the ratio of peak inverse voltage across the diode in a center tapped full wave rectifier and the bridge rectifier? Yes, what is the ratio of PIV rating? Peak inverse voltage means PIV rating across the diode in a center tapped and in a bridge rectifier. So they are asking PIV in center tapped. Center tap means midpoint tap, midpoint rectifier to the PIV in a bridge rectifier. What is the ratio? In center tap my PIV is 2 Vmax. In bridge rectifier my PIV is Vmax. So what is the ratio? It is a 2 na? Ratio is simply 2. So correct answer is option A. Option A is the correct answer. Alright? Option A is the correct answer. Yes. Next. The average load voltage across a resistive load of a single phase bridge converter connected with 2 SCRs and the 2 diodes operating at any firing delay angle alpha and supplied at 200 volt 50 hertz is? Yes, they are asking average load voltage across a resistive load of a single phase bridge rectifier. Single phase bridge rectifier. But connected with 2 SCRs and 2 diodes. Tell me 2 SCR and 2 diodes means, can I say that this circuit is a semi-converter? Yes or no? Semi-converter. Alpha is the firing angle and supplied at 200 volt. So my supply voltage RMS value is 200. What is the V0 average for semi-converter which is feeding to resistive load? Which is feeding to resistive load. What is V0 average for semi-converter? V0 average is equal to Vm by pi into 1 plus cos alpha. 2 SR 2 diodes na, means it is a semi-converter simply. So it is Vm by pi. Vm is 200 root 2 upon pi into 1 plus cos of alpha. Alpha is, yes, simply in terms of alpha they are asking. Yes. So my answer is 200 root 2 by pi into 1 plus cos alpha. Yes, what is correct answer? 200 root 2 by pi into 1 plus cos alpha. Option C is the correct option. Alright? Yes, some of you already posted the answers. Good. So it is Vm by pi into 1 plus cos alpha. Alright? Next is single phase diode bridge rectifier supplies a highly inductive load, means load current is constant. Highly inductive load means your load current is a constant. I0 is equal to capital I0. The load current can be assumed to be ripple free. The AC supply side current waveform will be, yes, single phase diode bridge rectifier feeding to highly inductive load. How is my source current waveform? Can anyone? How is my source current waveform? Diode bridge rectifier. Yes, 0 to pi and pi to 2 pi. During 0 to pi, which device conduct? Diode D1, D2, and pi to 2 pi, D3, D4. This current is I0 and here it is minus I0 na? Right? Yes, so your answer should be the square function, right? Square function. In case of thyristor rectifier, instead of 0, this waveform will start from alpha. Difference between thyristor rectifier and diode rectifier is, simply put alpha 0 degree in thyristor rectifier, you will get diode rectifier waveform. Okay, so it is a square function. So correct answer is option C. Next, a 3-phase fully controlled rectifier fed from 200 volt 3-phase 50 Hz supply is fired at alpha equal to 45 degree, the average output voltage is, yes, which converter? 3-phase full converter, 3-phase full converter, fed from 200 volt 3-phase supply and alpha is 45 degree. The average output voltage, 3-phase full converter, V0 average. What is the output voltage expression? It is 3 VML upon pi into cos alpha. So simply it is 3 into VML is 200 into root 2 upon pi into cos of alpha. Alpha is a 45 degree. Right? So you can write here it as 3 into 200 upon pi into root 2 into cos alpha is cos 45 1 by root 2. Root 2 cancel out, so you will be getting it as 600 by pi, right? 600 by pi. Simply directly based on your output voltage expression they have asked the question, okay? So answer should be 600 by pi, 600 by pi, alright? Next, a half-wave thyristor converter supplies a purely inductive load as shown in figure. Single phase half-wave controlled rectifier, load is purely inductive, right? Load is a purely inductive. If triggering angle of the thyristor is 120 degree, means alpha is 120 degree, then what is the extinction angle? Beta. What is the beta value? As I said, in single phase half-wave rectifier, the important loads are R load and purely inductive. So they have asked these type of questions on purely inductive load. What is the conduction extinction angle beta here? Come on, you can post your answers in a chat box. What is my extinction angle? What is the expression for beta? Beta is equal to 2 pi minus alpha, na? 2 pi minus alpha. 2 pi is 360 degree. Alpha is 120. So 360 minus 120 is nothing but 240 degree. 240 degree. Alright? So therefore it is option A is the correct option, right? Correct option. Next, the following phasor diagram represents the fundamental components of voltage and current on AC side of 3-phase controlled bridge rectifier. The mode of operation is, yes, rectifier, inverter, bridge idle or amplifier. Come on, tell me. Now alpha is here greater than 90 degree. So what is the mode of operation? Yes, you can post your answers in a chat box. Tell me what is the mode of operation. Is it a rectifier mode or inverter mode? Alpha is greater than 90 degree. Yes. If alpha greater than 90 degree means it is inverter mode, na? Check while discussing the important points in AC to DC converter. I have written one point, inverter mode operation. In inverter mode operation, I have written the required conditions also, na? In that one condition was alpha greater than 90 degree. So here alpha greater than 90 degree means it is a inverter mode operation, right? So correct answer is option B. Option B. Next, the output frequencies of a bridge rectifier and half-wave rectifier respectively are, where Fin is the input frequency. They are asking output frequency means output ripple frequency. Output ripple frequency. Yes, tell me what is output ripple frequency. First is for bridge rectifier. Bridge rectifier will give you how many pulses for one input cycle of supply? 2 pulses. So in bridge rectifier, output ripple frequency is 2 times the supply frequency. And in half-wave rectifier it is same as that of the supply frequency. So correct answer is 2 into input frequency and input frequency. So here answer should be option A, right? Option A. For half wave, this is simply equal to input frequency, and for full wave it is 2 times input frequency. All right. Next, yes. single phase full wave bridge diode rectifier delivers a constant current of 10 ampere to the load, means load current is constant. And which rectifier they are talking? Single phase full wave diode rectifier. Average and RMS values of the source current are, yes, what is the IS average and what is the IS RMS they are asking. Diode rectifier source current waveform, just now before the question we discussed na, my source current waveform for diode rectifier is square function 0 to pi it is I0, pi to 2 pi it is minus I0. This is minus I0 and here it is plus I0 na. This is pi and 2 pi. What is the average of this? Average is 0. And what is the RMS? For square function RMS is nothing but its amplitude na. So my IS average is equal to 0 and IS RMS is equal to I0. I0 is 10 ampere. So it is equal to 10, right? So correct answer is option D. Alright, option D is the correct option. Next, single phase full bridge diode rectifier feeds a resistive load of 50 ohm from a 200 volt 50 hertz single phase AC supply. If the diodes are ideal, then the active power in watts drawn by the load is, yes, single phase full bridge diode rectifier they are talking, resistive load, right? Load is now resistive. 200 volt 50 hertz supply RMS value. Single phase AC supply, if diodes are ideal, then active power input. Yes, that is P input they are asking. Here tell me if you are having the diode rectifier, this is my VS RMS is 200 volt and load resistor is 50 ohm na, 50 ohm. Then what is the P input they are asking? For diode rectifier, what is your output voltage waveform? Diode bridge rectifier output voltage waveform is this type na, pi and 2 pi. Yes or no? So what is V0 RMS? V0 RMS is simply equal to VS RMS, which is equal to 200 volt, right? 200 volt. Now can I find the P input, which is equal to same as that of the P output? Because in your circuit you are having only ideal thyristors na, diodes. Diodes are ideal means power loss in diode is 0. So my input power is equal to simply output power. And how to write output power? V0 RMS square by R. V0 RMS square by R. Alright. So simply put V0 RMS value here, 200 square by 50. You will get the answer for this question. Right? Yeah. Next question. Yes. Single phase fully controlled rectifier is supplying a load with an anti-parallel diode as shown in the figure. All switches and diodes are ideal. Which one of the following is the true for instantaneous load voltage and current? Yes, tell me the correct option. Which one of the following is true for instantaneous voltage and current? If freewheeling diode is connected across the load, can I get the negative load voltage? Can I get negative load voltage? No, na? Right? For what purpose we connect the freewheeling diode? To avoid the negative pulse in output voltage. So if I connect the freewheeling diode, my output voltage will be only positive, this type. Yes, my output voltage is only this type of nature. This is alpha, pi, pi plus alpha and 2 pi, right? 2 pi. So my output voltage is always positive, greater than or equal to 0. And for rectifier circuit, not only this rectifier, but in all rectifiers you can check, my load current is always positive. Load current is always positive. Any rectifier circuit you can check. Half wave rectifier, full wave rectifier, semi converter, 3-phase rectifier, everywhere I am getting the load current only positive. It is not possible to get the negative load current rectifier circuit because whatever the switches we are using here, these switches are unidirectional switches. If I want here negative current, means that current should flow through either this or through this path or through this path. But whether these devices allow the reverse current? No. So always keep in mind, in rectifier circuit, my load current is always positive. But load voltage can be positive or negative. It depends on your circuit. In this case, I am using freewheeling diode. So I am going to get only load voltage positive or 0. So correct answer is option C. Right? Option C is the correct option. Okay? Right. So friends, these are some questions from my side. Okay? So we are running out of time. I am giving my contact details. 7387864360. Right? You can message me on WhatsApp, okay, or text message me. I will share you the PDF copy of these questions. Again, after this, few more questions are there. I have shortlisted some of the questions. Please try to solve those questions. Even I will share my notes, okay. Those will be helpful for your preparation, okay. Right. Even my mail ID. Yes, it's Rajendra Gharase @gmail.com. Okay, you can send me mail or you can WhatsApp me. I will share the details. Okay, right. All the best for your examination and thank you. Thanks for watching.